Okay, so we are now going to start talking about vibrations and waves. All right. Now, the first part of this chapter, what we'll do is we're going to look at periodic motion, and within periodic motion, we're going to look at a subcategory, a very specific kind of periodic motion, which is going to be simple harmonic motion. Okay, we'll develop all the stuff for that, and then we'll use ideas from that to study wave phenomenon and other things. So, first of all, periodic motion. Okay, so any repetitive motion is going to be periodic. So if you have, say for instance, this is going to be one of our examples. If you have a spring and you attach a mass to the spring, and let's say that you pull this mass and then you let go, and assuming that there are no frictional forces, what we know is that this mass will undergo periodic motion, and this motion will keep on repeating itself, and we can figure out things like or we can define things like time period, frequency, and all kinds of things for this motion, because it will keep on happening again and again and again. Okay, so that's one example. Another thing that we will study will be also, let's say if I have a string and I have a mass attached to the string, and I let go of this mass at any angle, and we'll be and we can ask actually, what will happen to the motion. We know that the motion will repeat itself again and again. It'll keep going back and forth. Now we'll look at a very specific kind of this simple pendulum, but for purposes of periodic motion, we know that this will be periodic, assuming that there are no frictional forces. So the mass will always come back to the same height, and then it'll go back down on this side, and it'll just keep on repeating itself again and again and again. So we have many instances of periodic motion. Another example would be, say if you have a star and you have a planet that goes around this star. Okay, this motion is again going to be periodic. It's going to happen again and again and again. We can again find time period and all kinds of things. So there are many instances of lots of examples of periodic motion happening all around us. And let us define a few things. So one of the things that I've already said a few times is define what a time period is. Okay, time period is the time for one complete oscillation. Okay, let's make sure that we understand this. It's time for one complete oscillation. Let's understand this in the context of a mass spring system. So let's say that I have a mass, okay, and I attach this to a spring, and let us say that we have extended this mass already. Okay, let's say we extended by some amount A. We'll give this a name. Actually, we're going to call this the amplitude. Okay, and if I let go of this mass, okay, we know that this mass will initially start moving to the left. Okay, so it's when we let go of this block, it's going to start moving to the left. Okay, and then it'll keep moving to the left up to a certain amount, and then it'll start heading back. Okay, now one complete cycle is going to be, let's say, from the block starting here, going all the way to the left of the equilibrium point, and then coming back all the way to its original position. So that would amount to one complete cycle. Okay, so this is when the block starts at the end. On the other hand, let's say that we start the block at its equilibrium position instead. Okay, and what we do is, instead of pulling it, we give it a kick. So we give it some kick, and this block starts to move either to the left or to the right. Okay, so in this case, what will happen is the block will move all the way to the right to its to its amplitude, to the highest position it can be, and then it'll start coming back. Now remember, when it comes back here, this is not going to be one cycle. This is in fact only half a cycle. What we need is, we wanted to come back, go all the way to the other side, and then come back. So here in this case, the cycle would be the block starting at its equilibrium, going all the way to the right, going all the way to the left, and coming back to equilibrium. So that would amount to one cycle. So it'll be going all the way to the right, coming back, and then going all the way to the left, and then coming back. So this would be one cycle. Alright, so understand this, and make sure that we physically know what's going on. Alright, so that's one thing. Another thing we can define is frequency. Okay, and it essentially means how many times per second. Okay, so the number of oscillations, okay, so frequency is the number of oscillations per second. And we so we measure this as in 1 divided by seconds, but this is an important quantity. It has its own unit and it's hertz. Okay, so H-E-R-T-Z, hertz. So this is, we can relate frequency to the time period very easily, and F is simply equal to 1 divided by the time period, or T is equal to 1 divided by the frequency. Okay, so this is a relationship that's going to keep coming up a lot, so let's make sure that we understand this. There's another quantity that will come up, and let's, it's probably a good idea to just say it and define it. We've seen this quantity, we gave it a slightly different name. There's another quantity called angular frequency, and it is equal to omega, and it is basically nothing but F divided by 2 pi. Okay, and we can also relate it to the time period. T is equal to 2 pi divided by omega. Okay, all right. Now I made a mistake here. This should be 2 pi times F. So 2 pi times F is omega, or F is omega divided by 2 pi, and then T is equal to 2 pi divided by omega. Okay, so these are some of the things. Another quantity that we will define before we move on to the main part of the chapter will be the amplitude. Okay, and the amplitude is simply the maximum value that the position can take. Okay, in case of a mass spring system, or in case of a what's it called, the pendulum system, it will be the highest angle possible. So it is the the highest value taken by the position, coordinate, or the angles. Okay, and it all depends on the type of system that you have. Okay, so max, it is the highest value that will be taken by the wave. Okay, if you want to think of it as whatever wave you have, it will be the highest value that will take the greatest value. Okay, so if we have some kind of repetitive motion that looks like this, where the motion just repeats itself again and again and again. Okay, so here this is going to be the amplitude is going to be this highest value here, A. Okay, we could have another kind of repetitive motion, which will be, let's say if I take a ball and I drop this ball from a height h, okay, and this ball basically has a perfectly elastic collision with the ground, then we know that after it strikes the ground, this ball will come back up to its original height, and this motion will be repetitive. So we can keep repeating this again and again, and the motion will look something like this. Okay, so in this case, once again, the amplitude, we can think of it as the height h for the wave. Okay, another case, and this is the one that we're going to actually really focus on, is going to be when the behavior is sinusoidal or cosinusoidal. And in this case, the amplitude, something that you guys have already learned in your pre-calc class, the amplitude will be simply this maximum value. So it will be minus A, it will be plus A on the other side. This motion, the last one, okay, is going to be a very special kind of motion. Alright, this we're going to call simple harmonic motion, the hero of this chapter. That's what we're going to be looking at, simple harmonic motion. Okay, the other guys up here, they are not simple harmonic. These are not sinusoidal behavior. Okay, this one's a triangular function, this one's a parabolic function, just repeating itself again and again. This one is simple harmonic, and this is basically what we're going to be studying in the next video.